So welcome everyone. It's really nice to see all of you here today. Today we're going to start with our second server-side chat. And today we'll have a new subject with Martin. But first, I would like to speak a little bit about the server-side chat. So the server-side chat is our meetup group that we are starting. We started 2 months ago with the first presentation. This is the second, and we'll continue at least every 2 months. We'll have presentations, and the idea is to have presentations about DevOps, backend engineering, and data. Everything related to what runs in a server, like say. Also, we want to build a community. So if you want to speak, if you think that you have a nice topic, reach us. There's our names. I'm one of the co-organizers of the group. My name is Daniel. If you want to host, also to be in your place, in your company, I don't know. Yeah, just reach us and we can organize it to build a strong community here in Eindhoven and region. So I think that's it. I'm going to stop talking. I'm talking too much already. So I'd like to introduce Martin from Frank Energy. He's from Argentina. Used to work here at Waze 3 years, 4 years ago?
2 years. 3 years ago,
3 years ago,
yeah.
for 3 years. And now he's bringing this amazing subject for us. So please, the floor is yours.
Thank you very much. So, yeah, as it says here, we are going to speak a little bit about forecasting and optimization in an energy company. So my idea is to bring you a bit of what is being done in an energy company to maximize profit, be green, and help customers reduce their cost in the energy bills. It will be probably a high-level introduction to many projects. I will be speaking a bit of optimization algorithms, a bit of machine learning. I will go high-level. We have time if you have any question or some during the presentation, just raise your hand. And we can go a bit deeper if something is very much of your interest. So that being said, welcome. I think we just did it. We'll speak about the energy market. I will explain a bit who the actors are, what processes occur, what type of prices occur during the processes. Then we will go a bit about day ahead forecast. That's one of the projects we are making using machine learning. Then we will go a bit beyond the day ahead forecast in the energy sector and introduce you to what is an intraday market. It's like the stock market, but with energy, which is quite cool, and it's all over Europe. So yeah, people can make a lot of money out of it. And then we'll enter more in the optimization of energy in each customer's houses using the strategic energy management. And finally, I will introduce a bit smart homes and what optimization algorithms can be used there. So without further introductions, I will skip the welcome because I think we just did. Thanks everybody, of course, for being here. Waze also for providing the space and the food. So let's begin a bit with the energy market, how it works here. So in the last couple of years, there is less and less dependency on the gas, which was considered like a cheap source of energy. And it's more and more important in this independence to use more renewable sources like wind power, solar power, and be self-sufficient with those type of inputs because gas is no longer as cheap as it was. So in this whole new way of providing energy, there are a lot of participants. There are regulatory help me with this, entities in the Netherlands. There is also one big operator for high voltage network, which is called TenneT. And there are low voltage operators, which are the ones that take the electricity and gas to your houses. And then we have the energy providers that don't physically take the energy, but you make the contract with them, and you decide then the price per kilowatt hour, etc., etc. with these providers. So I'm working on one of these providers called Frank Energy. One particularity this provider has is that it has dynamic contracts. Dynamic contract means that instead of arranging with you a price per kilowatt hour, and in the end of the month just count the kilowatt hours, multiply by the contract price, and just apply to you, in every hour it charges you for your consumption using that hour's price. That's different. So instead of just arranging a fixed price contract with a certain price can be lower or higher depending on the market's price. It can be better, it can be worse, depending on the market. I mean, if you arrange with a fixed contract, a very cheap contract, then you are in a good position. But if the market prices become lower, you will miss that opportunity. So yeah, it's a different type of contract. In general, it's better, but well. So what is these market prices per hour and how that is determined? So every company, like Frank Energy or all the energy suppliers, need to forecast how much energy their portfolio of consumers will use tomorrow. They may use energy or they may provide energy. If you have customers with solar power, for example, in a sunny day with low consumption, they will most likely put energy on the grid. And most of the times what the consumers will do is take energy from the grid. So what all the suppliers must do blindly the day before of the delivery is to tell, I think it's to this high voltage operator, I'm not sure who, but we need to inform what the consumption and production will be for the next day. Then, when all the information from all the providers is there, this entity determines, depending on the expected consumption and the expected supply by the energy producers, the price for each hour of that next day. And that's how the day-ahead price, or also called APAX price, is determined. It's a function and algorithm based on all the expected production and consumption for the customers. And then we have imbalance prices. What happens with imbalance price? You, for example, everybody the day before expected a lot of sun, but suddenly when the delivery day comes, it gets cloudy. That happens quite often in the Netherlands. So really the network and all the producers expected not to have to produce that much, but clouds are there. So in order for all customers to have electricity, the producers must go and start producing energy, for example. Or you want to incentivize suppliers somehow to have their consumers use less energy. How do they do that? Through imbalance prices. So the energy must be produced, but must be taken from reserves, from different ways. And depending on how the extra energy is obtained, is that the imbalance price will be higher and higher. So consumers will not pay for that, but the energy suppliers will pay for that. And that what they pay in the imbalance market is the difference between the volume that they actually consumed and the volume that they said the day before that they would consume. It's more or less clear how the imbalance prices are made, how the APAX prices are made. Nice. So that is why it's very important to have a nice day-ahead forecast. You need to know every hour what your portfolio of consumers will do, will produce, or will take, so that you minimize the risk of having to buy energy in the imbalance market or to sell energy in the imbalance market. Sometimes you bought too much, suddenly it's all sunny, your consumers don't use energy, they put a lot in the grid, and prices become incredibly negative. So really the government and the entities are pushing companies to do something with the extra energy, giving very negative prices. So to not fall into this market is that, through prices are trying to incentivize competition in companies to handle this. Because, the government doesn't have all the infrastructure doesn't have batteries, doesn't have ways to deal with this extra energy. So they use companies for that. So this is why machine learning in this sense is so important, to try to minimize exactly the delta in the forecasted volume and what will be the actual volume consumed. And in the end, if a supplier is good at this and they can minimize the imbalance cost, then that can be also translated to users, giving cheaper contracts, making better competition, because with better prices, of course, more people will join your company. So a bit introduction, because machine learning, but how does machine learning work for this? So I brought just a little example. This is of course not the production code we run, but at least it's some explanatory code that, if you didn't work with machine learning in the past, can give a small introduction to what it does. So we have features. Features are all the attributes that you will use as temperature, solar radiation. And then we have like a data frame, or just imagine this as a table. We have that one day there was 25 degrees, 500x of solar radiation. This was the day 2, Tuesday. Minute of the day, for example, and what the consumption was that day. So this is all your training data. You imagine you have all this information for the last couple of years for all your customers. Then what you want to do is to get in this X all the parameters for the different days. In Y, I'm putting the result. Given these parameters, this is what happened. Then typically when you're trying out some algorithms and tuning them, what you do is to create some training set and some test set. So you divide this in 4 pieces. Okay, you use some portion for typically 80-70% for training, 20% for testing, if your training was correct. Then you pick a model. Here I'm putting linear regression, but there are many different algorithms for different uses, and depending on the features mainly, is that you prefer one or the other. Then you feed feed the model with all the historical information, and in the end you can directly predict given the test. So you have a portion of the data frame just for testing, just to see how it performs. So with training, you train. With test, you know what to expect. So you can check later if your model was correctly trained or not using the tests. So how many of you had worked with machine learning this way, doing the coding? For those who already work with machine learning, I think this is obvious. For those who never saw machine learning, it's a bit demystifying. It's very nice and can be very easy done. Now, if we go for different type of algorithms that can be used, here I'm using linear regression. Linear regression, what it tries to do is to find a few coefficients that, when applied to all the training data, generate the minimum distance to all the training set. So it's quite costly to train, but in the end, the entire model, what you persist, is just a formula. Just the coefficients is all your linear, your model. There are other options, for example, using other algorithms which can be more precise, especially working with categorical features. For example, here I'm using day of the week, 2, 4. In a linear regression, 2 is more than 1, 3 is more than 2, and that for days of week, that doesn't make so much sense, because at 8 a.m. It's never Wednesday more than Tuesday, right? But the shapes, the curves can be different in different hours of the day, depending on the day of the week. So that's where categorical features come, and then there are much better algorithms for handling those. That could be tree-based or decision tree-based algorithms, or k nearest neighbors algorithm, which handle these categorical much better. So in decision tree, what it ends up creating is, or what it tries to do, is to generalize all the input data or the training data with rules. Okay, it generalizes, and the more it generalizes, you can be underfitting, overfitting if you generalize too little and have all too big of decision trees. So it requires a lot of tuning, but for this type of problems with categorical things like holiday, etc., it's much better. And if we want to understand k nearest neighbors, it just tries to find 5 other records, 5, 10, or k, that are most similar to the one I want to predict. So the problem with that one is that every time you have a new record to predict, you have to go probably for the million or millions of rows there, get the distance with each one of them, and then say, okay, these were the 5 nearest, but it's quite costly at prediction time. So depending on the use, it can be useful, or it is too much work. Any question regarding this, or nope? Okay. So does it work? Yes, that's the good news. So in this one, for example, we see the correlation. We have what was the forecast in solar power and the actual solar that was for a certain set of days. The forecasted solar is in light blue. The actual solar power was in dark blue. And there in the actual consumption from the customers, this is typically in summer, because you see that during the day there is negative consumption, meaning a lot of production. You see usually the dark blue is more solar than forecasted, then the intake into the grid is deeper than the forecasted. And that occurs for every day. Here, for example, we have the other way around. It's there was less sun than expected, so production was less, so consumption was more. And this type of patterns we see very often, and the correlation between the forecast and the actual. And this is of course not house by house that you can do, but this, in case of Frank Energy, we have in the Netherlands, or at the time of doing this, a portfolio of 30,000 customers or houses. So in the 30,000, averaging works pretty well. So intraday trading. So we understand now how machine learning helps shaping the consumption for the next day. We do our beats, our reserving energy for the next day in terms of volume, but that has an issue. This is the day before. So during that day, until the delivery day, and during that delivery day, forecasts change, events occur. So what is offered is the opportunity for companies to exchange their positions. So for example, if one company bought too much and they realize the next day, and another company bought too little, they can agree on a price and interchange their positions. And that's how the intraday trading is made. There is a full market, really, with brokers and everything. So energy companies can buy and sell capacity or volume. And this is done even not only limited to the Netherlands, but also you can exchange or trade energy with other parties in other parts of Europe. So it's all interconnected. So this is what intraday is for. And one other big advantage that intraday trading has is that I mentioned that the Apex prices are made per hour. But imbalance prices, which is what the company, the supplier needs to pay in the end, are done by quarter of the hour. So when you pay for an hour, let's say, I don't know, 5 megawatts, yeah, but in the first quarter of the hour you had 6 megawatts, in the second and the third one, okay, you had 5, and in the fourth quarter you had 2 megawatts. You are always forced for paying what happened in the first quarter and in the last quarter. And the two in the middle can be okay. And when it's peak hours or when the sun is rising or falling, these curves are really steep. What makes that those volumes can be potentially very big. So doing intraday trading allows you to reshape what you originally forecasted hourly in quarters. So yeah, you reduce the risk of imbalance just by doing this. Plus, you have during the delivery day updated forecast. You can run your model and update your consumption forecast as many times as you want. So what does it do in practice? So here we see in light blue is the hourly day ahead forecast. In dark blue is the actual power consumption and production measured from our clients. And in orange, we see what intraday trading was actually trading. So for each one of the quarters, we already see that there is a difference when the light blue was going more square in quarters. The orange already goes every 15 minutes, but also is also much more near the dark blue, which is the actual consumption, what was measured from the consumer meters. So yeah, what big advantage brings this is that if we check, for example, I don't know, any moment in time like this, in imbalance, if we don't do intraday, we pay the difference between this dark blue and this light blue. And doing intraday, we only pay for this. So, and imbalance can be huge. To give you an idea of amounts, if APAC's price is typically in 200 euros per megawatt hour, in imbalance, it can be 1800 per megawatt hour. And that occurs many times a day, like 6-7 times a day, especially in the summer. So you see the big difference that suppliers need to pay when there is some imbalance. Intraday trading helps you a lot preventing that cost. Of course, the trading is trading, so the bids and offers can also be high. But usually it's much safer to check the risk in the imbalance in the intraday market, where you can say, yeah, I'm not buying, I'm waiting for imbalance. But yeah, if you go to imbalance and the imbalance is huge, you're screwed, you have to pay. So in intraday, you can still decide, depending on your strategy, what to do. And then we come to any doubt regarding the intraday market? Yep, clear. Yep.
What happened in the middle?
Thank you. Between 29 and 30?
Here.
No.
Well, this was a very good day.
A little bit after 30.
Oh.
So there we see that intraday prediction is under the dark blue line.
Yeah, so intraday we do periodical. Day ahead is always 1 day ahead for the next 5 days. We move 1 day for the next 5 days. So that's always like that. Intraday, you try to do more and more frequently. So depending on when you did the latest forecast, it could be similar to the day ahead. It could have changed a lot in regards to the day ahead. It's when you did the forecast. And also one other thing that can happen is that there is no liquidity in trade. So even if you want to buy...
Yeah, so it looked like you wanted to trade, but there was nothing to trade, so you went back to your prediction.
It's not that you go back. It's like if the forecast for a long time remains very similar to the day ahead, you will probably not move from where you are. Suddenly you see that the forecast changes, and then you want to buy, but probably everybody saw that the forecast changed in one direction, so nobody wants to offer the energy at the low price. They can put a super high price, and probably we say, nah, that price we're not buying. We will check our chances probably intraday. So even if there are offers, or we may not take them. It depends. And also, it can be a wrong, I know, King's Day. That can happen. I'm sure that King's Day, if it's sunny, if it's that changes a lot what happened with the actual versus the forecasted. Yeah, Frank Energy has a couple of years of history, but in these couple of years, there were not many King's Days. There were only 2. Probably the 2 were sunny. Who knows what can happen, if it's raining on a King's Day. So, this we can be far in some days, and that's part of the game.
I'm curious how the customer have access to this information. They have like something like this?
Good question. So, customer doesn't see imbalance. Imbalance in this part. Customers price that they pay are based on APACs. That's how dynamic contract works is based on APACs. So they pay the APACs price plus a fee plus some tax, but that's based on APACs. All the difference that there is between APACs and imbalance, that's paid by the supplier. So as we will see in a couple of slides, user can make or take some benefit out of imbalance with different projects. But in this one, this is all for the company. So the company adjusts their volumes and everything, the objective of all is minimizing the volume delta of what they forecasted versus what is the actual consumption for your portfolio. So we are not making a financial profit. It's not the primary goal to make a financial profit out of the trades, but to reduce the volume. There are companies, of course, whose business is making a financial gain out of it, but as energy suppliers, it's forbidden to speculate. You cannot speculate. Yes. So all the movements we do is always with the objective of minimizing the volume delta. There are many companies doing that, but they don't have customers. That's the big.
It's a different business.
Yes. It's using the same platforms probably, but different line of business.
The Intraday is focused on reduce wasting and the overcharge, correctly? So they use the intraday trading mainly to find the between of those two.
The intraday, what it tries to do is, if you were too short and you are realizing that during the day that you bought too little, is to be able to get from other companies that bought too much at a certain price that you can agree on the market. So doing the intraday trading, what you do is to reduce what you will have to pay in the imbalance. Because if you bought 200, in the end you use 600, for example, in the intraday, if you bought at least 400, in the imbalance, which might be the most expensive, you only pay 200 instead of 400. So it's a way to put you closer to the actual consumption in your portfolio.
But can happen, for example, the situation that I bought way too much and I didn't use, so I have like extra electricity.
Then you need to sell it in imbalance. And sell it in imbalance may mean sell it at minus 1,800 euros per megawatt hour. Selling with negative price means you have to pay for getting rid of the energy in the imbalance market.
That you already bought.
Yeah. And you don't use, but other companies are also not using. You are overwhelming the grid, and the high number is on your name. So you have to pay for getting rid of that.
And you produce waste in that sense.
I'm not sure exactly what happens with the energy itself. I'm not sure on the physical part what happens with that. But you lose money for sure.
I have one more question: is how you as a supplier know that I sell my overconsumption to him? It's like a platform.
Yes.
Then you have a platform and say, hey, remember I sell my energy to them.
So I don't know. We use a broker in the middle, but there is of course a platform that concentrates all this market.
We will see that in the coming slide.
No, I don't think so. But there is. It's a market. Like if you want to go and buy and sell, it's a market. I don't know what if you need to have a company or how it's made, but yeah,
Probably is regulated. Yeah.
one can trade. If you know what will happen, you can also lose a lot of money. So strategic energy management. Until now, we saw how the company with the portfolio of consumers tries to forecast properly. In Intraday, how we are trying to fix what we see. Hey, we're not going well to avoid falling in imbalance. But what do we do with the energy? I mean, can we, apart from trading and do all these financial things, trying to minimize and forecast, do something with the energy? Yes, we can. Along with the consumers have electric vehicles. Consumers can have home batteries now. That's growing. So yes, we can use consumers' assets to fight imbalance, and also now, yes, consumers can also take some benefit out of the imbalance. How? So there are a few implementations in Frank Energy. One is a virtual power plant. This is the first project that we made with this purpose, and it's steering the electric vehicles when the energy is cheap, and stop steering when the energy gets expensive. So many providers offer this using Apex price. In the case of Frank Energy, what they added is, let's also use the imbalance price and share the profit with the user. So it's that's one of the implementations. Then we had trading home batteries. This is something growing, and now Frank Energy also is offering batteries for those who can afford it. And using imbalance, they found that probably the return of investment instead of 10 years like it is when you just do self-consumption. With the model in the Netherlands, I will speak a bit later, it can be 5 years or less. So, and then we have smart homes, which is integrating not only electric vehicles and home batteries, but also with expected consumption, expected solar, and using different models depending on what you are trying to optimize and what the model in the country is, because it's not the same everywhere. We'll go over that in a bit. So virtual power plant, or VPP, how we call it, is the user needs to steer their car and leave their house tomorrow at 8 a.m., for example, or every day of the week at 8 a.m., except for weekends. So they can put that in the application. And then when we detect that the user plugged in the car, we make a plan for that. That would be the cheapest plan for the user, using Apex only in the beginning, so that we can guarantee the user will pay the least. But there is this imbalance benefit, right? So, when we detect that, for example, the Apex price is quite high, but we see that the imbalance is super low, we can start steering the car. We compensate the user for not using the cheapest Apex, and a fraction of that imbalance difference. So everybody wins. We are helping imbalance, user gets some money, we get some money. So it's and the user bonus is based on this Apex difference, like compensating and then paying on top, which is better than what most of the providers will do, is to get the cheapest hours Apex and use that. We can go a bit beyond with this imbalance charging. Any doubt? So, here we see you see how crazy the imbalance is. You have in green Apex prices. This is the day before. In yellow, we have a lot of signals of what's happening with the imbalance market. If we take, for example, this evening, in evenings is usually when all our consumers plug in their cars. You see that session grow. But here, if we take a look, here imbalance was significantly higher in general than Apex. If we go to what's happening with the sessions, yeah, we are not charging cars. And we are saving a lot of money in imbalance by not steering the cars if we have time for steering later. And in this case, we had, right? Next evening, imbalance is around Apex. So that's not so marked, but it's more like, yeah, all evening charging. Also here, we start charging quite a bit because here imbalance was quite low. Then imbalance high, then imbalance, yeah. At some point, we need to charge the cars. That's why always before 8 a.m., it becomes higher. And then we have this other project, which is trading home batteries. There is a very nice thing in the Netherlands that the energy you put on the grid, you put it, you take it, and it can only depend on price when you want to put it or take it, because there is no extra tax for taking energy. So it's symmetrical. You just need to take when it's cheap, put when it's expensive, and you're making a profit automatically. That's how the Dutch market works. In the future, that may change, but for now and for a few years, this is the business here. So when you think in home batteries, what the first thing that comes to your mind is, okay, I charge when there is solar power, and then in the evening I use it. Yes, but I mean, even if there is no solar power, you want to charge everything you can cheap, and you want to discharge everything you can expensive. If there is solar power, more money. But that's it. There is no incentive here for self-consumption. That's the model in the Netherlands. That's what's happening. And not only that, if you can also use for the consumers all the imbalance prices that you get during the day, and make sure not only in Apex prices you make this type of charging and discharging, but also react on the imbalance signals that we get. Yeah, then all the imbalance benefit can go directly to the customer. We could take a fraction of it, and everybody would be happy. So, yeah, here is some examples of how it goes. It's like, again, in yellow you see imbalance, in green you see Apex, and you see what the battery is doing. Here, where imbalance goes crazy, we discharge everything. Here it's kind of stable. Here it gets super cheap, so it charges everything it can. Here imbalance is much, or not much, but relatively lower than Apex, so it will not discharge. It discharges here when imbalance is a bit higher. And also, how fast or how slow depends on how imbalance is at that moment. Any doubt? This is quite, it's not much logic, it's just cheap, do it, expensive, do that. There's no algorithm here. Not a sophisticated one at least. And then we get to smart homes, because not all Europe is like the Netherlands. So what I mentioned about symmetric conditions are not in all over Europe. For example, in Belgium, they charge you for taking energy out of the grid. What that means is, if you just take when it's expensive, when it's cheap, and put when it's expensive, it's not always beneficial, because depending on how much that tax is for taking, and you're not recovering for putting, it should be very big so you can make a sufficient profit. And the bigger the tax is, the less restrictive it is. So, and not only that, in Belgium also there is the peaks issue, that is that you get charged differently depending on the capacity of your house. So if your charging capacity or your consumption capacity is 20 megawatts, you pay a tariff. If your capacity is 10 kilowatts, you pay different tariff. And how is that determined? It's determined by the most taking quarter of hour that you had in the whole year. So if at one moment you were charging your car and charging your battery, that will survive the whole year and you will pay much more. And the same way, discharging. So you don't want to discharge you don't want to use too much of the solar power and discharging the battery at the same time. Because you enter in the same situation that you reach a peak and that moves you to a different kind of user. So you cannot do that the same that you would be doing in the Netherlands of not caring about what's happening in the whole house. So you need to be much wiser in that on that regards. So some implementations to handle these type of situations. First is cost optimization. You can do some optimization. For Netherlands, you can do it blindly because there is no limitation. But for Belgium, you need to take into consideration the tax. Probably doing something more similar to self-consumption is preferable. And self-consumption, most battery providers will have a hardware implementation or something running locally that checks all the energy that's going on in the house and try to limit that before going to the grid or checking from the grid. Or you can have some forecasted for self-consumption and adjust with the readings real time. And this one can be price aware because if you're going to use all the energy you have, you could use a bit more extra information regarding the price in the moment to decide to postpone the consumption and to use a bit more from the grid, for example. So it can really deviate you if you have some type of forecasts. So how do we do optimizations? Because now it comes to algorithms. As a general thing, you want to optimize two things. I mean, some things you cannot change. You cannot change the solar power in most of the cases. You cannot change, or we are not trying to change the home consumption, like when the user is doing the laundry or watching TV. So those things we are not going to change. We are not targeting to change, but we are going to try to set what the EV power is in every minute. So when do we charge the car in every minute? It will be 0 or 10 kilowatts, for example. And the battery power at every minute. That thing also we can control. And that's what we are trying to control. So for these optimization algorithms, what is the grid balance? I mean, you will be charged or not, depending on how much energy is coming and going from the grid. So simple calculation is, the balance is what the house is consuming, the power that you are using for charging your car, the power you're using for steering, also your home battery, minus the power that comes from the solar panels. So this simple calculation is, what is the grid balance in every minute? Okay, that's what you try to plan. And then you need to choose what you're minimizing. Okay, in every optimization algorithm, there is restrictions, and there is something you want to minimize or maximize. In this case, if we want to minimize cost, what we need to do is to minimize the sum of all these balances in every minute times the price at that moment. Okay, and that will bring the minimum cost. Or in case of you want to minimize volume, if you want to go for self-consumption, even if you are using the prices in the calculation, you want to minimize the absolute of these balances because you don't want to either charge or discharge. You want to take that to 0 as much as you can. So we can speak about a couple of different type of algorithms. One very popular and fun to try is the evolutionary algorithm or genetics, and another that is very used in optimization in factories to solve the traveler's problem, to plan production in factories, is linear programming. And then, yeah, we can see how we adapt that to our problem of EV power and battery power. So to talk about genetics, how does it work? So you start with a population of individuals, like could be thousands, millions. Each individual, what is each individual in our problem? Well, one individual is each one of the EV action sub I and battery action sub I. So the array of all of those two arrays in every minute, that is our population. Then we can check that population, every one of the individuals that could be random to start. You put them in the fitness function, and that fitness function will say how good that solution is. So depending on what you're minimizing, yeah, the one that costs the less or the one that produces the less grid interaction will be will get a point, some amount of points. One thing to notice is you will penalize all the non-viable solutions. For example, if your entire solutions end up charging your car more than needed, that one will take long value, long max value. Or if, for example, the battery goes beyond the limits, yeah, that solutions you want to directly eliminate. And that you can use the fitness function to do that. Or you can be smarter at when you generate the population, you can already give some indication of what is a valid individual or not. Then you check this generation, can be a few million individuals. You select the best, those that got the best points in the selection. You make them reproduce. You change a bit of bits there, so you get some mutations. And then you repeat. You have a new generation after these two operations, and you get a new generation, and you repeat the process for an n amount of generations. Could be 500, could be 1,000, depending on how sharp you want to do. The big advantage of this type of algorithms for optimization is that this fitness function can be anything. Like literally, it's a function. You can choose what to do, what to evaluate. If you want to call APIs in the middle, you can. If you want to read the database, if you want to multiply the variables among each other, there is no limitation because the fitness function is yours. You do whatever you want. So it's an optimization that is super flexible, but because of the nature of this number of generations and individuals, it can be heavy to process. And also, yeah, unless you make a big processing, it tends to have local bests that don't meet each other. So, and always the ones that are going far and mutate from the local bests always tend to come back to their local best. So, and you may miss global best. Those are the odds of the genetics algorithms. Any doubt for this? Yep. And then we have one much more used when possible. That is linear programming. Linear programming, as I mentioned before, is very much used in factories for project planning. You can put in all your restrictions as inequations. For example, we have a set of developers. Okay, this guy can work 8 hours. This guy is going on vacations. This guy knows this technology, and this technology. So those are the limitations that you can express, or you should be able to express as inequations. Typically, inequation, like for example, this guy this month has less or equals 20 hours. In our case, an inequation for the energy will be the sum of all the charging intervals plus the initial charge cannot exceed 20 kilowatt hours. That is the capacity of a battery. So you express all the constraints as inequations, and then you have your minimizing or maximizing function. In our case, it's usually a minimizing function. We want to reduce either the volume or the cost. So what it brings in the end is quite complex to model sometimes when you have a very difficult problem. It's always doable. but you fall into a lot of tricks. For example, here I bring you one piece of trick for minimizing the volume. We say we want to minimize the absolute interaction with the grid. So either putting from the grid or checking from the grid. If I want to minimize what I interact with the grid, minimum is minus infinite. So that's not my intention. My intention is to keep it as close as zero as possible. So what I do here, for example, for this trick, I create an auxiliary variable. I add to the model that each one of the minutes of this absolute balance should be greater or equals than the balance. The balance with the grid, remember, can be positive or negative depending on if I'm taking or putting. So, and I also add this second inequation, that this absolute should be greater or equals than minus the balance. So I'm sure that this will be positive, and I am sure that the absolute value will be higher than the absolute of this. That this variable will be always bigger than the absolute of this. And what I minimize now is not the volume. What I minimize now, knowing that the absolute variable is bigger than zero, I minimize this, the sum of all these absolute balances. Does it make any sense? It's quite complex if you're in, I understand, but yeah, you fall into all these type of tricks. And linear programming, for optimizing what it is based on, you express all the inequations with greater or equals or minor or equals. That ends up drawing something like this. This is 2 dimensions. But if you think of every EV action and battery action sub E, all of those are dimensions. So you can end up, every minute for a couple of days. You have many, many dimensions. And so what it does, this linear programming algorithm is go through, because this is linear, goes only through the edges of the inequations and then executes the minimizing function with the intersection of those, and it knows that it will find the optimal value in one of those edges. And here, for different algorithms, we can see some different behavior using different modeling. This is taking only price into consideration. So this orange one, for example, the battery, in the price one, you will see that it's always square. So cheap, here are the prices. If it's cheap, I charge. If it's expensive, I discharge. I don't measure how much. I just use all the power all the time. This is a simulation on a hardware reaction device. So it will only charge, green is the solar, orange is the battery. So here it can only charge, and this one, blue, is the state of charge of the battery. So here in the hardware simulation, you can see that the battery only gets charged when there is sun, and when there is consumption, that is a yellow one, and there is no sun, it will use the battery. Here, this day, there was more sun, more than the solar power. Indeed, so it goes all the way up. Then here, that energy is utilized. So it comes back. So hardware means react to the actual consumption, doesn't know anything about price. Price doesn't care about consumption or production. It just uses the price for going up, down. And this one is a smarter algorithm that sometimes it uses full power, even more than because this is price aware, so even more than the solar is giving. But many times it doesn't go all the way if it's not worth discharging all the energy. So it knows when to hold some energy to charge later. And all these are made with the same algorithm, just modeling a bit differently for the optimization. And that's pretty much it. So yeah, if you're interested some moment in joining some energy company like this,
Please, a round of applause for my team.
so any question?
Yes, any questions?
Yeah, sure.
I have a lot of questions.
Okay, so let's try to solve most of them at least.
Yeah, the first one where machine learning basically are trained and modeled by you, right? You feed with data and then you project what will happen.
Yeah.
What is the role of intelligent artificial intelligence?
No.
No,
No.
it's only with machine learning.
Classical machine learning. Yeah.
Yeah, but don't play any role in this projection. Cannot fulfill any.
It helps during the development, but
but
but-
a projection.
no, not for this at least. No. And not currently. Yeah. Maybe someday we will find a good use. For now, it helps, yes, on the development time.
Yeah, but not in the projection itself. Only in the build of the model.
Yeah.
All right.
The part of analysis of data is really by human.
Sorry?
So the human, the who analyzes the data and who takes decision, that's a person, right? That's
No, that's pure machine learning.
so the whole process is automated, and based on that, the machine control the whole flow. And
Yeah. So yeah, for automating, we have tools, of course. We use Apache Airflow a lot. That's a very, for most of the things, for forecasting and all that, that's more than enough. Then Python. So
one of the questions, when you presented the genetic algorithm, you said that you added some mutations on the new generation.
Yep.
What are the mutations that you add? Because I usually, when I was checking genetic algorithm, I know that we create random data and you input information, but how do you input data on energy consumption? You know,
yeah. So what is an individual here? Individual is a combination of this minute I charge, this minute I don't charge, this minute I don't charge, this minute I don't charge. So mutating in this case means grabbing one of the winners from the previous generation and just saying, you were not charging here, charge here. So that's mutating. And then mixing is getting half of the values from one individual that had a good score, half of the intervals or the values of another individual, and just create a new individual with halves of them. If it's a valid individual, it goes to the.
do you use the
Fitness
same
function.
algorithm in other scenarios, or just maybe in various charge to discharge?
Sorry.
Do you use the genetic algorithm in the other cases, or mainly on that one?
No, it's for this, for optimization. It's one way specifically for optimizing stuff. Yes.
Thanks.
Yep.
Any other questions?
Your presentation showed two machine learning algorithms. How are you really combining them? Do they both work in parallel or sequentially?
There is one machine learning algorithm. So we do one training every day that we get data from our customers, and then we use the same model for running over and over for the intraday trading.
Like there was the genetic and linear programming.
That's not machine learning. That's pure optimization algorithms. It's different type of. Yeah.
Thanks.
Any other questions?
Where do you process all this information you have?
You stole my question.
Where this magic happen?
In Google. Yeah, GCP mostly.
Yeah.
So
There is also another cloud providers. There are many applications for different parts of the project, but basically cloud computing.
So if I can complement your question, that is what I would, because I'm a more DevOps cloud engineer side. So what's the tech stack, main tech stack? I saw it's Python, but databases, cloud services. If you need to choose 3 or 4 that
Well, BigQuery we use a lot. BigQuery is super flexible. You can scale very well. It's used widely. For machine learning, we use probably the most popular library out there, that is scikit-learn. That's very popular. Then, yeah, Apache Airflow, as I mentioned before. We do a lot. We have robust workers, so we can put the workers to work with heavy, intense stuff. And then, yeah, some applications, we have them also in TypeScript. That is part of the stack, running in Node.js. Yeah, and that's pretty much it, right? For Frank.
How do you manage those stuff? Because it runs in batch, it runs out the day. How does it run? Because you said the machine learning process runs, but I imagine that you have a lot of IoT devices or something that receives the information for everything. So, and Google just shut down their IoT department. So, do you have this IoT part?
That part is not in Google.
Oh.
The IoT, that is part in Node.js. So yeah, we have nodes, we have with high availability, several instances running. So especially for the charging of the vehicles, we have a provider that every update there is on every car, they send us a webhook call. If we fail to respond, they will retry a few times, so we know the latest status of each vehicle. And that's with an actual application running in one of the services. So.
Nice. Any other questions? Okay, I'm going to ask only more once or twice.
How do you control? Oh no. How expensive is this in production? Like analyze this data, the Google factor, the Google bill at the end of the month is too expensive.
To be honest, I don't know what it is now.
But it's in the order of a couple of hundreds, I think.
Maybe you're reaching now
800.
7 to 8.
Per month? Per month? Really? Oh, but is intentionally like that, or should you run? Oh yeah, this is, or you are really controlling all this?
I mean, I try to avoid doing too much that I don't need. In each process, we try to do the minimum possible. But yeah, sometimes we need to move data, we move data.
Yeah, but how did you reach that level of, well, need to run only this precise model this time? Because I can imagine that when I need to take measurement of all the ecosystem put there, you need to really process a lot of information and running.
Yeah, I mean, for training is probably the biggest part. Training, because we do really move the entire data set. We have pre-selected the features that I know I will use, of course. So I'm not bringing the entire set of features we could use. That's probably the biggest movement of data. And then for forecasting itself, once you have the model is a file there, a few megabytes. So remember the model, for example, we use tree-based solution. So it's just an abstraction of the entire data set. It's not that we use that data set all the time, the training. So we have our model, and then for forecasting, it's just nothing from the history. It's just the next hours or the next day. So in that moment, the data we move is not that much. That process, every time we forecast, can cost cents, I would say. The expensive part is the training, probably.
Yeah, interesting, because in my head, this is really expensive.
It can even be cheaper because they don't notice everything. In this 700 to 800 includes the whole setup of Airflow.
Yeah, also there is a lot of financial processes and a lot of things that are not even related to this. So and probably those are the less efficient processes.
Thank you. I have one more question, but I will come.
Yeah, okay. So for more questions, let's go for the drinks and networking and pizza, if there is any there. So again, a round of applause for my team. And Now that's an awkward moment that I need to promote to the next server-side chat, and it's myself. So, so that's a little bit awkward. But the next one is gonna be here as well on 20 June, the same time. I'll be talking about more about DevOps and actually infrastructure as a code, and with no YAML and no JSON for developers. So how to engage developers on the infrastructure as a code side? Yes. So that's the goal of this presentation. I did once, and it was focused on AWS, but now I'm going to be AWS Azure because I got some feedback from the last presentation. So if you saw the last presentation, it's not going to be the same. Okay. So that's it. So I think we are done. Thank you, Martin. Thank you, everyone, and see you on the next one. Bye.